All right. Today we'll talk about some more vector processing. Basically, we'll go through a bunch of examples, try to get a handle on how to develop vector-style programs in preparation for the next homework, which will be some sort of vector processing of integers. And then I've started preparing. I think after that we'll do a bit of GPU programming, take a quick look at sort of SIMD in a GPU context. And maybe if we can slip one in, we'll see. If there's time, we'll have a homework on that too. Not sure. Maybe a bonus homework. Okay, so last time we were doing this thing. We were computing a sum using this parallel add. It's a very simple start, but it's have to start somewhere. And some question came up after class. Like, why do we bother with this if these vector instructions are slow? So I think maybe I've mischaracterized this a little bit. It's not that vector instructions themselves are slow. Once you have data in the vector registers, basically all of these run in one cycle. In fact, what's his name? What are they?
I think it's Agner Fog.
Agner Fog, thank you. Whoa. That's a big alert. Let's take a look. So we were using this VP add B, right? So let's see if we can find it. Are we on the right architecture? Ryzen, that's AMD. We're mostly working with, well, all right, let's look for Broadwell. That's one we've been sort of using as a reference. They're not very big differences between them, but might as well stick with the same. And our vector instructions should be coming here. Here we go. Right, so here they are. In this case, maybe we want to think about reciprocal throughput, that being how many you can run per second if they don't have any dependencies. So you see for, let's see, did we have an add somewhere?
Per cycle per second.
These are cycles, yeah, latency in cycles and throughput in cycles. Let's see, I was hoping to find that add, p-add, here it is. Okay, so half a cycle is what it takes to do this parallel add. Right? No matter what size. And so what does it mean that it takes half a cycle? Well, we can do 2 at a time. Right? We have 2 of these adder operations available in any cycle. And then the latency is 1 cycle. That's nice. Some of them take a little longer, like these with the H, horizontal add. Those add across values within a register. Those are always slower than the ones that go between registers straight down. Yeah, I think that this means that we have 2. Actually, I'm not sure, because for normal adds we have a reciprocal throughput of 1/4. So we can do, and we have 2 execution units, and each can do 2 per cycle. So I'm not exactly sure what happens there. But anyway, you see most of these instructions are really fast. Some of them, okay, take a few cycles, maybe in latency, right, to do a comparison for all of them, but at least we can run many at the same time. So if you write your code cleverly, you can basically run most of these instructions once per cycle. Not maybe Not these gather ones are funny ones. There you tell the CPU to pull in values from many cache lines into one register. There's a I think I don't have the details, but basically it's lots of extra memory access there, so we could ignore it. We could ignore those for now. You see, most of them are really, really fast. Okay, so today I wanted to do a couple of things. First, I thought we'll take another look at this adder part and kind of finish it up. This is nice. The parallel add is great, but this part is awful. Maybe performance-wise it doesn't matter, but let's figure this out. Let's just get a complete sum done in assembly or with vector instructions. So here we're talking about, if this is a short, it's not a gig, if this is a shorter array, then suddenly this is not an important part of the execution. Now this one becomes pretty big because you have 32 times around this loop that we have to complete. You should be able to do much better than that. Okay, so how do we do that? There's a few different instructions that kind of help us with, but I think, okay, let's do it this way. Are we dealing with bytes? Okay, I haven't done an example on bytes, so this will get exciting. So I made some drawings here in preparation. So we want to compute the sum. In this case, there's no byte-wise sum. In fact, I'm not sure that we can do the B at all. Shuff B. Oh, that's okay. That might be okay. All right, per bytes. All right, so basically we have a bunch of sums. I guess 32 sums, right? But let's work with 8 sums because it's easier to draw it. I'll make this a little bigger. So perhaps these are the sums. Now we want to compute the sum of these sums. And so far we have a for loop, but there's no vector work in there. That's kind of boring. So what's some other ways that we can compute the sum? Basically, we want to kind of add them together horizontally. Now, unfortunately, there wasn't a horizontal add, and maybe that's nice. Let's see. There was a ph add. Look, there's no ph add b. Right, it does. This is signed. This says word, so that's 16 bits, and D for 32 bits. It just doesn't do it for 8 bits. Okay, so we're going to have to work something out ourselves. Okay, so let's see. Why don't we do? If we take a copy of this. Now I'm doing this for a smaller register, but I have faith that we'll find the right instructions for byte-wise as well. So, and then we kind of swap these around. So I take a copy of it and swap it around, and now I can do a vector add again, right? So now I have the sum. It's actually identical. You see, these two, the sum of those, it's the same as the sum of those. It's just kind of swapped. So if I add these up, now I have just 4 sums. I used to have 8. So in 2 instructions, one instruction to do the swap, and then one instruction to do the parallel add again. Now I have only 4 sums, so we cut it in half. From 32, it's much better, right? Now we went in the same, one instruction to do the swap, one instruction to do the add, we went from 32 to 16. We're really saving some time. This instruction is called Permute. So some handy vector instructions. Permute. Swap 128, or swap upper and lower parts. The one we're interested in is called v perm 2I 128. All right, so it's we're swapping two 128 pieces. That, or in this case, if these were 32-bit registers, right, we're taking all of it, all of these, and putting them in the upper part of the destination register, and then we take the upper part of the source register, putting that in the lower part of the destination register. Okay, so why don't we just try that out? In fact, in order to kind of write this stuff, it's a little hairy, right? There's lots of puzzling going on here. So how do we debug this thing? How do we develop this stuff? I think one good way that I found is to try to work step by step and look at the intermediate values. There's two things we can do. We could run it in GDB. We'll do that later, perhaps. And that's really good for debugging. Like when you have all of the code and there's something wrong, then you can step through it. That's really nice. But when we're building new code, we can do it even easier with just printf. So we'll do that. I guess go like that. Char pointer sum. Okay, what am I doing? Here's this big sum array that we have. We know it's a packed bunch of 32 bytes. So I'm just casting that. We're dealing with a vector up there. Now I'm casting it as a character array. Same memory layout. That's okay. So I take the address of it, cast it, and I dereference it to get the value of the character at element I. All right, and then I guess we want a new line. So I found this to be really helpful to have this all set up. At least when you're kind of getting used to it. Okay, I'm going to use a different machine today. I think we may be needing some other instructions for the upcoming homework that's only available on this machine. So we'll see. Okay. Let's see, what is this? AVX2. Ah, okay. Didn't print a whole lot. Some ASM, are we not calling it? We are calling it. I'll just, we'll leave that in place. Am I saving this in the wrong place, maybe? Aha, my SSH thing is broken again. This SSHFS is awesome, but I wish I had something more reliable.
The latency is bad as well.
Sorry?
The latency is bad as well.
Yeah, it can be quite bad, yeah. Okay, all my servers, just like the class servers, they all use the same file system, so it doesn't matter which one I'm mounting from. Okay, so maybe now it'll. Yes, please. Okay, yeah. What is this final sum? Is this something we were working on? We don't really have a good final sum. We'll just turn 0 for now. Okay. Wow, that's a lot of sums. Are these really? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I guess these are just kind of large numbers. I think those are starting at -1. Is that it? We're printing these as, actually, let's see, we're printing, how do we tell it we want to print a byte? Is it HH? Does anyone remember? Okay, that was good. All right. Okay, so I was printing out the format string says, okay, treat it as a larger integer. Now we're looking good. Okay, so these are the sums of our gigabyte array. Right? Remember, we're summing up with, we're kind of wrapping around the 256 maximum of our bytes, but that's okay. So now we want to compute the sum across these. Let's see. So what do we have? Right. So we have this already. So now if we want to swap the two, let's see how that comes out. Here's a nice way to write inline assembly, by the way. C doesn't care if you write a string like this and then another string, it'll just concatenate them for you, no matter how much white space you have. So it's much easier than trying to do like this maybe, or yeah, I like this way. Okay, so let's try to permute these. Okay, now we have to see the instructions, how to use this thing. Perm. That's the one. All right, so this permute, it doesn't just swap them. They decided to kind of build in lots of functionality. So in this permute thing, you actually have two source registers. We'll stick with one. We'll use the same source register. Both. And then you can select for each one of the destination upper and lower 128 bits. You can select which of all these four you want. And you select that by the 2 bits in this 8-bit immediate that specifies it. And basically each nibble says a number which you want. So it goes 1, 2, 3, 4, or 0, 1, 2, 3, really. So we'll say all right, so we'll figure out the numbers in a little bit. So from our two sums and then into the sum again. Okay, so these are the 3 operand registers, the 2 sources and the destination. We're just swapping things around. It. Actually, that's no good. We should swap it into a new register, so let's do that. YMM0, and now I have to tell it that we're clobbering YMM0, so the compiler doesn't use YMM0 itself. The compiler doesn't really know what we're doing in the assembly, so we have to tell it that YMM0 is no good for its purposes. So basically here, this one says, oh, put the value of sum in some YMM register, right? And I'm going to write back into sum by leaving a value in that register, and you better make sure that you keep that value later. That's what we're telling the compiler with a plus. It's going in and out, and the X says which kind of register. Vals here we're saying we want to read in the address of vals. Let's see, not the address, the value here. This value should go in another YMM register. But it can't be in YMM0 because we're using it. Oh, and by the way, if the compiler wants to use YMM0 anywhere outside of here, it has to save the values that it had in YMM0 before running the assembly, because we're going to be overriding it, right? That's what this whole clobber statement means. So again, it goes assembly stuff, colon, inputs and outputs, or outputs really, but if it's a plus, it's input and output. Strictly inputs, and then clobbers. Okay, so now it should be swapped. So how do we say that? Well, so we want to say in our upper part, that's this nibble here, we can choose between 0, 1, 2, 3, right? It probably shouldn't be 0 or 2. Those are the lower parts of both of the input operands. So it'll be, let's go with a, actually we want to swap them, so it should be a 0, and then it should be a 1 in the lower operand, the lower part of the operand, right? So we're saying, oh, give me this one here, and this one there. Right. Okay, so let's see if it went and swapped that for us. Oh, nice. What's it called then? I missed a 2. 2i 128. There it is. It's actually a little interesting. You may notice when you start writing this sort of thing, first you get your C errors, right? Bunch of C compiler errors. And then when you cleared all the C errors, now suddenly you start seeing assembly errors. Because the way it goes is the C compiler just doesn't care what's in the assembly block, right? It just plops it in the right place and then hopes for the best. And then you run the assembler on top of it, and then the assembler says, well, what's that instruction? Right. So we got, well, okay. Maybe we didn't quite see a demonstration of that. Okay, so let's run it again. And now, ideally, they would be swapped for us. Well, it's really hard to see where one part ends and the other begins. Let's run it again, just make sure it's deterministic here. It's not. What are these values? Did we not clear them or something? This really looks deterministic. Start our sum at 0. Looks like it produces all sorts of values. Okay then. This seems like it would be a good time to yeah, no, this all looks good. All right, probably a good time to try out GDB. Let's compile this with minus G, and then, okay, so okay. I had a little handy thing here. Oh yeah. Okay, so there it is. Okay, here's our add part. All right, and then we're comparing. This is going around the loop, adding the same stuff over and over again. Let's see, where are we jumping to? Why don't we step through a few times to see where it goes? Right. Okay, so here we're loading the values, the vals into YMM. We're incrementing RAX, that being the pointer into this R. And then we're adding, so YMM1 is where we have our sum. So let's print this. Ooh, that's kind of nasty. We can do better. Oh, sorry. And I don't know why, but when you're in this layout ASM, the GDB doesn't like to do command completion at the same time. The two are interfering. If anyone knows how to get command completion to work, that'd be great. I'm going to have to type it out over and over. Okay, so I'm saying YMM1, that says that this register in all sorts of formats, but if we tell it, in fact, I think I'll copy this so I can do it a little quicker. Okay, so in 32, in fact, I think we wanted, in this case, we want to be 32 into 8. All right, okay, so there's our sum so far. And let's take another step. Now we add it again. Oh, v32 into 8. Right, so it's a vector of 32 in integer 8s. Right, there it is. Take a few more steps, go through it one more time, and print it. Okay, so why are we getting random values? Huh, doesn't let you do that. It's too bad. Are we initializing it all the way? Ooh. To gig minus 1. What's that? Maybe that's the problem. No, it's still there. Damn it.
They're 8-bit integers, right?
Yeah.
And they were numbered 0 to 31.
Yeah.
And then, so 31 minus 30 over 2 is, I think you have overflow. 31 times 30.
Right? What?
2 is 465. But your largest number you get is 256, right? If they're 8-bit integers.
Yeah.
So
What am I missing?
So you're overflowing, right?
Yeah, so all these additions will overflow, but they're bitewise.
Right.
And in any case, they shouldn't be random. Or where are we overflowing? You're saying in the vector add we're overflowing?
Yeah.
Naturally, because there's tons and tons of them that we're adding up. There's a gigabyte worth of them that we're adding up.
Yeah.
But that shouldn't create any random values. Right, the overflow generally would just wrap around.
Mm-hmm.
So we're getting some. In fact, let me see. Maybe one of these other ones that we're running was actually writing to the memory. I don't know why that would be the case, but let's get rid of some of them, and we don't need to worry about that either. No, still happening. Oh, that's annoying. All right. I have another thing I wanted to do, and I think we'll just continue to that, and I'll try to figure out what's going on with. I think there's random stuff in the memory itself. I don't know why we would get that. Something about our initialization that isn't quite right, or maybe we're overriding it somewhere, or maybe there's something here in this pointer dereference. There's not a whole lot of places where we could go wrong. R is the one we're initializing. There really is not a whole lot that could go wrong here. Unless the sum was, no, the sum was fine. This was all zeros in the first place. Huh. Ah, that's really too bad. Okay. So I had another one that will be a little bit easier to manage. I want to look for a minimum instead. It'll be easier to deal with the numbers. The sums that keep wrapping around, they get confusing, and it's hard to get a good grasp on it, even if we had smaller totals, I would think. So let's just do another one here. We'll make it an array of integers. And we'll just have 1024 on. Set this. And to make it easy, we'll set them like this. But then we're going to set one of them to a different value. Okay, so the exercise I want to do here is we want to find the smallest integer in this array. It would be a little easier. I'd hope this something would go quickly, but sadly not. Okay, so we'll say okay. And in this case, we're dealing with integers. We have four. Let's see. We have a 256 wide register. So how many integers can we fit in there? Is it? Oh, I'm losing my mind. 8. Okay. Okay, so much like the previous case, we have an M256. We call it means this time. Just initialize it to, oh, let's initialize it to something big. In fact, I think if we go -1, let's see, no. How do we set it to something big? We'll do oh, we don't have to set it to something big. Why don't we just pick the first stuff from our integers? So first set of integers. Like that. Okay, and then I want to print this out. Just use the same one. Okay. Oh, and an int here. All right, so we're going to do something in here, of course, to produce the set of minimums, but let's just build this for starters. Doesn't like that. Which one? There should be an I in there. am I doing this for? M256i. Okay. Should get rid of the sum stuff. I think we're still printing that. Get rid of that. Are we really not having any luck with our initialization here? Integers I. What am I missing? It looks like this thing isn't pulling out the values the way I'd expect, but I don't really see how that would make a difference. All right, let's see. Let's just see if we're getting the one step at a time. Let's see, and this here. Okay, we have the right integers in there. That's good. So our mins, this all means the same thing, so I don't see the problem. Oh, aha. Let's see. Yeah, so this is the problem. Mins is a we can't use that as an array. I don't know why it didn't complain about that. So it should be like this. Right. Really? Crash and burn today. All right, folks. Tell me what's going on here.
We maybe run it through GDB and see if...
Where is integers initialized?
Right here.
Oh, okay.
And then we're running it. And in fact, we checked it. We printed it out up here, and it has the right values. Yeah, let's run this in GDB and see why. See what's actually hiding in our mins value. That's a good idea. I'm particularly confused because I tried something like this just earlier. Let's see. Where's our, oh, is this in ASM? Yeah. Okay. So let's see. Well, there's our printf. Oh, I see. So I think GCC decided to not put this in a that's what it is, maybe. It's not putting it in a XMM register at all. Right? There's no instructions that do what we want it to do. It's just, maybe that's it. So why don't we try just forcing it. See if the code turns out different. I think we'll compile this with GCC-S this time. And there was a really nice, what was it called? Verbose ASM. I thought this is pretty cool. Where are we? Min ASM. Okay, so with this verbose ASM, it puts in little comments with the C code. Sadly, a lot of other stuff too, but okay. So now I guess we can see something about what it's. Where's our NOP? There. Okay, so is it now it's loading that into YMM? Okay, that's good. Okay, I guess we can see what values go into YMM. That'll be a good start. Okay. I'll wait for our NOP. That's a good place. And now let's see what's in YMM. The 8 and 32. Okay, so they're there. That's good. So this part worked fine. So then it seems like our problem is here. Maybe it isn't a problem anymore, actually. Let's just, yeah. That's the optimizer for you. So it actually printed it out correctly now. Right. Interesting. Okay, so to recap, I think if we get rid of that, we get random values, and if we have a no-op, we get the values we want. Nice. That is probably a compiler bug that we could report to the GCC folks. But let's not worry about it. Let's try to learn something more about vector programming. Okay, so so we've read our first set of integers, right? But we want the minimum of all these integers in this big array. There just so happens there's a nice instruction called vp min SD. So vector with a V, that's a 256 wide, right? S for signed, D for double word, 32 bits. And with that one, you can tell it 2 different values and where you want to put it. So I'm telling it, we're going to accumulate the minimums in this mins. And then I have these other values in X. And that'll be integers. Let's see. Integers I. Okay. Almost. Right. But here, now it would take 1 integer, because integers is of type int. Right? It will take 1 integer and stick that into the lower parts of this YMM register. So we'll have to do our little cast again. We'll have to tell this is a M256I pointer. See, that's good, but probably need 1 more in here. Okay, I'll just break this out into more lines now, so it's a little more readable. Okay, so now we have the minimums. So it's kind of dull this direction. Why don't we go this way instead? Okay, so now we will have, for each iteration, mins will have the minimum of the previous mins, whatever is in the other register here, which is the next set of integers, and that'll be written back into mins. So let's see if we get that to work. Let's run it in GDB. What is a good line to break at? Maybe here. Okay, and so we are, YMM0 was the register that it chose for mins, and YMM1 was the register it chose for this other value, the stuff from the integers. So we can probably see it reading them in. 0, 1. Huh. Where's the read? In fact, maybe this is not where it's happening. Maybe it's oh, it should be. Where's the jump? 204. Yeah, so this is the loop. Aha, yes, sorry, it was in black, I didn't see it. Here's where we're reading in the values from the integers, taking them in, and then we're just going around here. I guess we're saving this to the stack for whatever reason, the min value to the stack every time around. That doesn't seem very optimized, but that's okay. So let's try to print. Oop. Okay, those are our current minimums, right? I turned it around at 1 minus, 1024 minus. So if we go a few times around this, let's see, just, so now it's still the same. Actually, not quite. A few times more. Okay, so it keeps going smaller. Let's put a break down here. In fact, I don't need to put a break. Let's just clear this and continue. Okay, so we found a bunch of minimum values. Right? These all look proper. These are as small as they can be. There's no 0 in there. I started at 1024 minus all the values up to 1023. So 1 is the smallest value, and then I set one of those to a -1, right? Just somewhere among them. So it looks like we found our minimum, but we also need to get the minimum out of these 8. And that's sort of, that brings us back to what we were doing with the addition, but I guess in this case, at least we have deterministic values in memory, so that's nice. So we'll go with that. Okay, so so now I wanted to, and it's a smaller set of values too, maybe makes it a little easier. So how do we get the minimum of those? There isn't, at least not in this instruction set that we're working on, a minimum that goes horizontally. There's some minimum horizontally for floats, I want to say, but there's nothing that we can use at the moment. So, okay, I guess it exited. That's okay. So how do we get the minimum across them? Well, first let's use that permute thing. Right, so we have our array of, let me run it one more time. Right, our array of 8 values. Why do they disappear when I scroll? When I change the size, that's weird. I should have a new line. Okay, so we have these, so if I swap these, put these in the upper in a different register and take the min again, then we'll get at least 4 different minimums instead of 8 different minimums. Let's do that. B perm 2I128, right? And we said $01. So this was, I want the upper part in the lower part and the lower part in the upper part. The upper nibble says which part we want for the upper part, and the lower nibble says which part for the lower part. Right, and then we're going from our min register and into our min register. Right, okay, it's a good start. Let's see, so now we should have 2 sets of did it get reversed? Is that what we're seeing? Man, it's hard to read this. It doesn't look reversed at all. Let me put a printf here. Actually, we want it in a different register. Actually, but yeah, let's try this again. Maybe we'll print them as unsigned. That doesn't help either. We'll just do it like this. So is this one the reverse of that one? Not really, right? So those 2 are the same as those, but overall it doesn't look very promising. Drat. This is crazy. Oh, sorry. Of course. So this was this loop here is computing the minimum over all of them, and now we wanted to do it at the end. We wanted to do our computation for the final last few values. Right, okay, so here it is. Okay, that'll do it. Okay, so the whole point of this was we want to find the minimum. So now we've got the 8 minimums, right? We were changing the 8 minimums along the way. That's no good. Once we have the 8 minimums, now we want to compute the minimum of those 8 minimums with a small number of instructions. Okay, here it is. So one thing we could do is we could take all those 8, we could rotate by 1, take the minimum, rotate by 1, take the minimum, and then do that 8 times. And then finally, if we've done that, now all of the values will be the minimum of all of them, right? In fact, maybe we should try that first. But I should demonstrate that this works first. That would be good. Okay, so there it is, rotated, or swapped. So those values are now sitting here, and those values are now sitting there. Okay, so now if we want to take the minimum of a pair of those, right? We take the minimum of those and those, and let's just stick these values in another register. Like that, and then we'll say the same thing again. VP min SD and $0. Okay, so now we should have 2 sets of minimums. That. Where did my terminal go? Somehow I managed to switch screens there, and the terminal went away. Okay, I'll make a new terminal. Okay, so now we should have 2 sets of the minimums. All right. So we took we had the full set, we swapped it, and we took the minimum of those pairs, and now we end up with 4. So now how do we get from these 4 to just 1 minimum? Well, I guess we could try a couple of different things. So why don't we do this rotate thing first, just to see how that works, to get a new instruction. It's not ideal because it's 8 steps. Right? Now we're not using vector instructions really anymore, but I kind of like the instruction. It's called VP align R. So let's give that one a shot first. And I'm just going to comment these out for now. I guess we need the min SD. Yeah. So I'm saying let's take. So VP align R. It's a cool function, cool little instruction. It takes 2 vector registers, puts them back to back in a huge 512 kind of temporary buffer, and then rotates by a number of bytes, and gives you the lower 256 bytes of that. So in our case, because we're using the same source register for both, it just becomes a rotation function. But you could use it for other cool bits and pieces too. So I'm gonna rotate it by 4. And then we do the -d of, let's see. See what happens. Actually, I think we got a little lucky. We have 2 -1s. Let's continue doing this. So here I rotated it by 4 bytes. Actually, why don't we, let's see, what does it look like without this? Just to make sure I'm not telling you lies. Okay, and then we rotate everything by 4 bytes and take a minimum. How do we end up with? How do we end up with a -1 there?
What is it? Is it a circular rotate or is it?
It looks like it only rotates in the top. Let's take a look at the rotate. It only rotates 128 bits at a time. That's a common thing that they're doing. For whatever reason, many of these instructions, they work in lanes of 128 bits. So the shuffle, which we'll see in a moment, will shuffle any order within 128 bits, but it won't go across the boundary to the other 128 bits. This, the one we just used, the Permute, it swapped 128-bit pieces, right? It doesn't swap within it. For whatever reason, I guess when they first built it, they had 128, and then it kind of got complicated to extend it properly to 256. So they kind of made it a double 128 register instead. Okay, let's find this align R. So this is what it does. Right? It takes your in fact, that's what's going on. Yeah, so it rotates within, this is poorly laid out here, but these are the top 128 bytes, top 128 bytes from source 1 and source 1 and 2, and then it does the same thing for the lower 128 bytes, so it rotates independently those two. Well, okay, that we can work with that. So now, if we do this a few times, do it 3 times, then I think we should have the same minimums all over. Oh. Right. Yeah. So I rotated just these 4 by 1, by another, and we take the minimums across, then we end up with the minimum in those 4 and the minimum in those 4. But we want the minimum across all of them, right? Okay, any ideas? Well, we had our permute. So one option is that we get now, so now we have these values. We swap those into a different register, take a minimum across those. So now we get, ideally, we get all -1s. Look at that, yeah. But this is quite a few instructions. So if we're trying to optimize this, we really shouldn't be doing it linearly, and it's much worse if we're doing this byte by byte, right? It would be terrible. So we need something a little better than that. Right, so I think we'll start with our permute, because that kind of gives us the biggest bang for the buck. See, so there we had what, 6 instructions. Let's just put our permute back. And now we're stuck with 2 sets of these identical values. Okay, So what else can we do? There's an instruction called shuffle. Right? The shuffle lets you, within 128 bytes, arbitrarily reorder all the values. So let's see, maybe with this drawing we can figure something out. Just move this out. In fact, we only get to do 100 within 128 bytes, so we can stick with 4 values. Right? And we want to be able to compute the minimum vertically. So we need to have all different combinations of A, B, C, D. We want all of A, B, C, D, ideally in each of these columns, right? Well, at least in one of those columns. So I guess one option would be to shuffle like this. Right? Take the minimum of those. So now this actually means, so we're going to have, so these are the same. The minimum of those is the same as the minimum of those. So now we have 2 minimums left, right? If C is the smallest of A and C, then we're just going to have C. Right? If D is the smallest of D and B, we're just going to have D here. So we'll have 2 values. If we take the min of these 2 sets, we'll have 2 values left. So let's figure out how we can do that. And shuffle is a fun operation to deal with. So let's try that. So you can find the instructions for it. Shuff. We want the D for double word. Okay, so here you go. Shuffle actually works on, again, on these 128 byte chunks. So it'll do the same shuffle for the 128 upper bits and 128 lower bits. All right, so we wanted to reorder them. And the way you get to specify it in this one, it's not as nice as with the 2 nibbles. That was really a nice encoding. Here it's 2 bits at a time. So the lowest 2 ordered bits specify which one we want here, between 0 and 3, right? And then the next 2 ordered bits, which one do we want here, and so on. Okay, so let's start by just writing out the instruction. So it takes an input and an output register, VP shuff D, input register, and an output register. And then we need to get this figured out. All right, so it's 4. In each one of these digits, we specify 2 of those positions. All right, okay, so what did we say? We wanted these 2. Okay, this one should be position number 2, right? 0, 1, 2, 3. So that's position 2. And this one is position 3. So 3 here, that is 1, 1, right? And here is 2, 1, 0. 1, 1, 1, 0, so E. The lower order bit nibble should be E, right? And then these, okay. That's position 0, that's easy. And this is position 1, so 0, 1, 0, 0, right? That becomes a 4. Okay, let's try that. So now we've done one shuffle. Okay, we're getting there. 2 instructions, down to a remaining 1 that we need to figure out. Okay. Any ideas? Yeah, we could shuffle again, right? We could just shuffle. See, just flip like that. Rotating does seem a lot easier, right? Because figuring out these bit patterns, little bit of a pain. If we just rotate, because we're anyway rotating within this 128, it'd be nice. It'll work just fine. So let's stick a rotate in there. We had it too. That's kind of ugly. Okay. So we rotate by one value. It's from the minimums. Yeah, that's about it. Right. So now we're going to have 1, -1, 1, -1, and another register. We'll take the min across. So that means we'll get all -1s. Yes. Okay. Right. So how many instructions are we talking about? 1, 2, 3, 4, 5, 6 instructions. Gave us the minimum of 8 values. It's not so bad. It's not so great either. So what would it take if we had with a for loop? Probably on the order of 32, right? Probably something like that. We have to go around the loop, and then we have to do if this one's bigger, and so on. It's probably like 4 to 8 instructions per time around the loop. And then there were 8 of those, so 30 to 60 instructions maybe.
You also would have had to write out to the cache, right? So you get a time advantage by staying in register C, right?
That's right, yeah. We don't have to write anything to L1, that's true. Yeah, there's certainly advantages to it, but as you can tell, there's a lot of fiddling to get it quite right, and knowing these instructions. So, in the homework, in the next homework, we'll do a minimum like this, but it'll be a fixed size minimum, and your goal is to find the index of the minimum, right? So right now we computed the minimum, but we don't know where it was. We just know what the minimum was. So to find the index as well, it'll take a little extra assembly, but basically we're halfway there, I would say. Okay, I think we have 1 minute left. Were there any questions on the homework then? Anything quick? All right, so it is due on Thursday by request. And good luck with that. I'll see you Thursday.